April 3rd, 2023. Well, let's see now. In the past day or so, since recording a brief essay of sorts, of a monologue, of a lecture, of the simulation of a course, of a narrative, of a curriculum, of a study, of a research, of an idea to learn about mathematics and foundations of mathematics, foundations of logic, foundations of a technical philosophy, thus that for reason and rational inference, there's arrived at a logic and mathematics. There's the idea of how it can be a science as well. The idea that this belief system is essentially a science, and that the higher order concepts of fundamental belief and faith are kind of combined. There's where faith is a sort of fealty or obeisance or abeyance, observance, while the belief is a matter of cognitive elements and ideas and thoughts and the process of communication or who knows what, and how that can be inferred from what you know or what one knows about what they say and this kind of thing. There's a usual course to consider how to arrive at that from fundamental principles, and in one sense that there's the observation of the canon, and all the greatest parts are what are arrived at from study and research and the search for these things. And the other one is about the experience, that it's really is only through the experience of learning and considering the bounds of reason and the study of things, and also the experience of the cost of when it comes to that. As humans, we have essentially bounded resources, and that could be time as the last resource. That the cost of making a study all the way from the foundations then kind of asks the question, what is that worth? The idea then is, for what it's worth, is that once there's generally something that can be found as satisfactory as a foundations, that's of inherent value all by itself, and that once there's reached a certain facility in the relating of the foundational elements of belief and belief in oneself, and faith in oneself, and in the belief and faith in the universe for nothing, so satisfying kind of the nihilist, satisfying the existentialist, and satisfying the objectivist. It gets into that also. It becomes a very fundamental toolkit for all manners of the application of reason. That is to say, from learning a bit of technical philosophy and answering life's question words as what is an answer, and figuring out that what it means for reason and logic, that there is such a thing and that it exists, and that it's constant and consistent and complete and concrete, and that we can attain to it even though our perceptions are varying, and otherwise some antonyms of those words, varying and not necessarily consistent, because things need to be made consistent or resolved, and not necessarily complete because we're not omniscient beings. That is yet as well concrete, or as far as our perceptions can advise us, that is as so. That we're basically closest to the concrete, and as well that as we reach for the constant, and that being of sorts what a foundations is supposed to offer is it's the fundamental bedrock of how to build all the rest of logic and mathematics and science. And that then for the exercise in reasoning, that suffices as something that's very well worth the value. And then with regards to what that means for that experience is first in the applied, in the practice of anything from computer programming to count and change, or working in the field of mathematics, or applying some things, or researching and studying and fitting more detailed pieces into a comprehensive narrative about really what they are. That it's knowing the names of things, that it's knowing the truth and inner beauty as what so arrives, that it's a fundamental exercise that most people carry on each day, and just as part of coping with the world. And then that the higher order apparatus of the vocabulary and the knowledge of the canon and the experience of the depths and wonders of thinking, plainly, end up being that it's something that then enables one, it empowers somebody, that he or her can then result as being at a higher level of existence, essentially. A more secure member of this rational world. So that's always amused me. And one of the key things that got into this thinking was that of the nature of the continuum vis-a-vis the nature of the discrete. Now, I had been very lucky when I grew up that I had been offered a if compulsory, a free public schooling, and that it was in the surrounds of a culture that valued that and had the resources to provide that, and that I was never lacking for the source of a linear curriculum that at least was designed to set me up for success in usual endeavors, and without much otherwise opinion. As I look back, in most all what I've ever studied and learned is really objectively knowledge itself, and that is not so much, not that anything is without viewing through a lens of culture or a lens of opinion, but it's as well that it was offered as very practical and free of judgment and opinion. And if I look back at my education, thusly I was happy that I never had to reject what was provided to me. I never had to resent that which was provided as education and instruction. But there are two things, and one of them was 0.999, and so at one point in time in school, one of the teachers said, "Hey, here's the fact for the day," and this teacher, the physics instructor or so, was often would like to open or close the class with something that was thinking exercise or something, and not necessarily on the curriculum, but of an enrichment in its nature. And the idea was that there's a number 0.999999999 infinite in extending with the ellipsis, that 0.999 is an infinitely long sequence of nines in base 10 or decimal representation. And then of course it was directly demonstrated that it's equal to 1.00000 . So 0.999 equals 1.000. Now I can see this because 0.333 is 1/3 its representation. If you multiply that by 3, it's equal to 0.000. And in a way, it's the same thing as 0.999. And then otherwise, given that 0.333 is a representation of 1/3, there's a couple of different ways you can write that out in terms of arithmetic, the arithmetic of multiplication, and that you can demonstrate that according to inductively carrying forward the laws of arithmetic as you carry what's called carry in arithmetic. The carry is it's what's left when you interpret each moduli as it's more and more precise, that what carries is what is called carry. And then that similarly when that arithmetic is in the more significant, where more significant is the higher orders of magnitude, or to the left of the radix, which the decimal point is called the radix, and also the base is called the radix. That what's to the left of the radix, in most significant, it has the carry of addition carries to the left. And then similarly, this 1/3, if you add it together, would carry all the way to the right, of this infinite sequence. And the thing is that the infinite sequence does not have a rightmost bit. It is unending. It is unbounded. It is we can only ever write finitely many terms of it, and we can only really consider it as a case for infinite induction, as we kind of talked about in this discussion earlier of the continuum and the standard foundations of real analysis. So I said, hey, there's another way to look at that. It's infinitesimally different from 1.0, and so in a clock arithmetic, essentially, that it rolls over, because there's a term that must end in 0.998, and then there's a term that ends in 0.999, and then that rolls over in what's called the clock arithmetic or the modular. That when you look at splitting up the unit into 2 many pieces, then 3, then 4, and then infinitely many, that's another way to describe the set of real numbers between those two, and the course of passage as of the constant uniform motion of time between 0 and 1, or as it would constantly be made in metaphor from the control panel of an auto vehicle, that the odometer rolls over and the last digit is representing the passage of that clock arithmetic, and as it rolls over, and the entire thing rolls over as if it carries. That's of course only in the finite. That it only represents a fixed point rational number. Yet at the same time, it would represent this in extremis or ad infinitum if that were so precise that it was measuring a continuous quantity between 0 and 1, and that it goes from 0 to 1. Or in this case, 0 to 999, and then rolls over back to 0 again as well. But that's a bit beyond when we talk about that. Besides that, we can talk about 0.999 as a manner of speaking and a manner of writing a number, and that a real number like 1.000 has a dual representation as a number like 0.999 ... That in another manner of speaking, there's a different representation of real numbers that happen to share the same digits and happen to share the same infinitely many initial segments, but have a different end or terminus. That was something that I rejected in that day, but I agreed that the other way was a thing, and didn't really care to carry a chip on my shoulder for the rest of my school career about it, but I did. So then I guess if there was another one of those kinds of ideas that I didn't accept after its instruction, there was what's the notion of called curved space-time, and things could diverge in space-time, and thus that there would be histories that don't meet or something like that, or that there could be the model of geometry where there's not the Euclidean space-time, and that otherwise there would have to be some mechanism why they came back together. And so these days, I all I know right now is that the current state of science has that the universe is essentially flat, and if there is a curvature of space-time, that it is essentially an infinitesimal. Kind of like we're talking here about the infinitesimals between 0 and 1, if there are in this model of real numbers as divided into the infinitely many, and that there's an infinitude of these numbers, and it's an exact infinitely many as projected from finitely many each one as they go on. That is so similar with the gravitational constant or cosmological constant of what results being general relativity's gravitational field equations, that it so results that this non-standard number has a real physical interpretation. So I was very lucky in that. And then I studied the notions of the continuous and discrete, basically with respect to getting calculus instruction and this kind of thing. And this served me well in all my classes that followed in coursework in college, like econometrics, use calculus. Probability and statistics, well, it starts with finite combinatorics and counting arguments and these kinds of things. And then probability theory, it uses calculus. And when we say calculus, there are many kinds of calculi. There's the umbral calculus. There are calculi of sequent calculus of logic and the digital and the binary calculus. Anything that calculates is a calculus. The integral calculus is this mensuration, as we've been talking about from the foundations of standard real analysis, as from discussing Hermann Weyls, the continuum, a critical examination of the foundation of analysis. And so in this manner, I had felt that I was very well served by the educational system, and that at the same time I was always kind of happy that I felt like that as I learned more about it, it just made more sense. So then when we heard various kinds of notions like, well, what if there's a multiverse and it's more than one universe, I could just kind of discard that as like, well, we just have the one we're in, and in the one we're in, we can theorize how it's so and keep separate this abstraction of thought, which can include absurdity and include error or that our mental model of how are we so perceive in our object sense, in our mental imagery and mental sense to be, that it's still so that there was something to attain to, that was some perfect monism, and that it's always been the case that there is a firmament, and that monism is very satisfying. So I went on to study mathematics and science, and then also in terms of like the representation of things in space, there's 3 dimensions, and so the field of computer graphics and 3-dimensional computer graphics has become quite a thing. This was in the advent of the era of things like realistic computer graphic imagery in motion pictures, or generally. And when I was in school, when I was in about 16, I went to a conference in computer graphics. It just happened to be that they were having a conference of a section of the special interest group on graphics at this one university when I lived in Oregon, or when I visited, and so I went to this conference hall, and I'd been familiar with video games. As a young boy, I'd spent all my hard-earned allowance and everything I earned from my paper route on stuff from my computer. I had the Commodore 64, which is an 8-bit CPU system with 64K RAM and a cartridge system and what was called a cassette drive. And it was available, one of the peripherals, a floppy drive, where these diskettes were variously 1 or 2-sided, single or dual density, 720 KB or 1.44 megabyte and upwards floppy drives, or the 5 1/4 inch floppy drives, and that also there was available for the system later the peripheral of the 3.5 inch floppy diskette, although it was a slightly improved cassetting in the cartridge in how it's placed. So I was familiar with the operation of my computer and programming it, and no great shakes by any means, but it was mine. And the facility of cartridges according to the contacts, and that they have storage and if not state, where unplugging the power, plugging it back in, recreated the entire state. Or with the notion of the cassette drive, where the tape cassette drive is basically, it uses the same media as what was an audio cassette, but it's stored on the medium, which is a magnetic tape, and it has magnetizable regions, and the tape head is able to interpret those magnetized regions as a sequence of a waveform or a sequence of digital or binary values. And it's also able to write such a value to the tape cassette that it's read-write media. That then also there was the other diskette drives and the disk drives, and these basically function in my world for load. That I was able to load star and it would bring up my game, and I was able to, in accordance with my buddies who all had a similar system. It was the premier system of the time for most people who wanted a computer they could type on, as it had a keyboard and it's integral. That the Commodore 64 is somewhere in a basement, and every few years when I dust it out and look at it, it's fundamentally operable. And the stack of 50 or 60 floppy disks that I collected all fit in the metal box that I fabricated in Metal Shop, where when I was given a project to fabricate something out of sheet metal with a press and a bend or whatever it is that makes the bends of the 90 degrees in the sheet metal, and a drill and a spot welder, that at some point in time I had enough diskettes for my Commodore 64 that I needed a box to put them in, and I made one. So carrying forward, as I got through school, I never really considered to study software engineering or programming as my career, because I figured that everybody knows that. So, but at the same time, later on when I found that I wanted something that was a portable skill set and I could find work in anything, it's that everybody knows that. So I went to study in the three-dimensional, and the three-dimensional involved the study of the mathematics of three-dimensional, and I've been familiar with the kinetics and kinematics of the two-body system planar. Most all our problems were presented to us in the univariate and planar. When we talk about related rates problems in calculus, or we talk about finding solutions in terms of time, or the tautochrone, and all these sorts of things that were presented as possible things to solve in calculus after setups, and equilibria in chemical reactions, or in econometrics, determining where curves meet of supply and demand as essentially models for economics and chemistry and physics and these sorts of things, that in three dimensions, then the solutions and the setups were much less contrived. So then when I first learned about the use of, there's rotation matrices, which are a subset of matrices that enable by the computation of linear matrix computations, a representation of a value as a directional vector in a 3D space, and then there's combined what's called translation and rotation. That given these two operations, that a change between one and two things would be a well-defined operation by these mathematics of an arithmetic of rotation matrices. And then I went on to learn that there's also the quaternions. Now the quaternions are rather like the imaginary numbers. They have three imaginary components instead of one, and they form an algebra, and they're closed, and they're products of the operations of arithmetic that we usually have. And then also that they suffice in terms of an operator calculus or the algebra about them, that their rotation is modeled in them. So you can fundamentally use the quaternion for, in these three representations of things by 3D mathematics, the quaternion. And so my study of 3D graphics and design of things, and And this was in the mid 1990s, so it's still about 8 or 10 years before video games and associated industry became a bigger industry in terms of capital and income and gross than the movies. Because, of course, at that time, movies was or cinema, as it were, but the production of movies was a bigger industry than video games, which was growing much more. And then that at some point in time after that, then the production of interactive material, more so than just that which is observed, actually has become a bigger industry than the movies. So, and then I studied this for a while, and part of that got me into studying the mechanics of three-dimensional interactions for chemistry and physics, or the fundamental operations of what are considered molecular modeling. Now, molecular modeling is the idea when it's hoped to determine ab initio, from first principles, how it's possible to determine for a given configuration that when these molecules are in the same solvent, say, that at the time the most difficult challenge was called the folding problem. The folding problem was that in DNA replication and the creation of proteins and the proteome, as after the genome, and the genetic machinery of the cell with regards to cellular replication, and also with regards to the creation of proteins, and as after enzymes and other active sites on molecules that interact in the intercellular and extracellular matrix of eukaryotes. That when I was studying molecular modeling, then there was amber and chyme and these sorts of things where there was looking to be solving the folding problem, and how hydrophilicity works. That water is a highly polar solvent. It's called the universal solvent, and water as the solvent, and that the solutes in the solvent behave very, very differently as with regards to when they are non-polar solvent. And so these kinds of things were the touchstones at the time of the folding problem and hydrophilicity. And so my studies really in molecular modeling, and also in classical mechanics and classical kinematics and this kind of stuff, then led to further study of these fundamentals in what are mechanics. And so at this point in time, I knew some things about some very, very rudimentary things about electromagnetism, and quite a bit about kinetics and kinematics, and was learning about the molecular modeling, and then also about things like cosmology, or the cosmological modeling. So sort of classical mechanics in the middle, including kinematics and the result of collision, and what happens when there's impulse, and all this kind of thing, with regards to then, and I'd studied basically the university background of including the humanities to an extent, of a science degree, of a university degree. That in this later discovery and research, I was more interested in the computational framework and the framework of standards, and also of definition and programming language, and the implementation of information systems with regards to anything. All this at this point included basically my view of what was physics in reality. So then I got to studying some more, and I became really interested in the continuum and the discrete, the continuum. And so I went to study the continuum, and one thing that we found from the continuum these days is that the key way that infinity is admitted into the study of the analysis is as a set theories, a regular and ordinary set theories, and this was discussed in the earlier discussion about the standard foundations of real analysis, that for Georg Cantor, who is this patron of a sorts, that set theory introduces a term that is an inductive set that has infinitely many elements in it. this is kind of in all of what has been talked about the actual infinity and potential infinity, that in all our works where we're attaining to that from our limited scrawling geometric means with our compass and edge, and perhaps a meter stick, that via these bounded and limited means, the only infinity was as yet of an abstract thing. That's the only thing admitted to the definitions of mathematics. So I was very curious to learn, then when I was studying the continuum about the real numbers, that the entire framework of the standard real numbers basically rests upon set theory. And it's fair to say that set theory is also, it's an opinionated set theory in a sense. Now, by opinionated, I mean that this regular, ordinary infinity of elements, an infinitude of these elements, is at once well-founded. Whereas otherwise, well-founded means that there's eventually a transitive closure that does not include itself. That this infinity that would otherwise be a specification of making an infinite thing would include itself, because it's infinite and it's one of these logical short circuits that happens automatically. That the opinion of set theory is that this does not. And so then the key theorem, after this establishment of what's otherwise kind of an inarguable expansion of comprehension, this restriction of comprehension, so defining only course and building a fence and saying there's not that other side of the fence, ignore the fence now and focus on this field, that then the key things are the results of uncountability, that there is the power set result in set theory, and then also from geometry there are various ways to establish that there's not a one-to-one and onto mapping from a set that's the integers, this inductive set, or omega, which has cardinality aleph 0, the first aleph number, and the power set of that set. And this was discussed a little bit more fully in the previous talk about the foundations of real analysis. So that the idea of the continuum is that the real numbers are written in that form, their expansion, the representation according to the complete order field, that they relate to the sequence of all the infinite sequences of zeros and ones, that there is a one-to-one and onto mapping between those, a bijection, that this bijection relates Cantor space of all the zeros and ones with the real numbers, basically is saying for all the real numbers are all the integer part in front and then the non-integer part after the radix. So we'll treat and we know that we can kind of scale those by 1 over x so that we can have a one-to-one and onto function according to 1 over x between this and that. And then we can double that a bit. We can contrive this tent of a set of functions that still have a function all across them, that the property of having the same cardinal is a transitive property. Any two sets that have the same cardinal happen to have an however contrived one-to-one and onto function between them. That can involve any framing of countably many different contrivances which so result to make it so. So then this was deemed, then the continuum hypothesis is that the cardinal of the integers, or here the natural integers. In this context, when I say the integers, I only mean the natural integers, as they call it, between 0 and infinity, not the negative integers. And it's only to indicate, for me, it indicates an integer continuum. But in the sense of ordinary regular set theory, it's this ordinary, well-founded set. And these are all technical words that must be used correctly, because ordinary and well-founded mean about the same thing. For example, while ordinary means also in terms of the ordinals, which have their own sort of set theory, own sort of theory, and are modeled in set theory. And well-founded means it satisfies that one axiom, and dot, dot, dot. That, between the cardinal of the integers and the cardinal of the power set of the integers, is whether or not that those are basically previous and next. And then there's the continuum hypothesis and generalized continuum hypothesis, in as regards to whether when the cardinal of the real numbers, which is labeled little c, when c, it's the cardinal of the real numbers is equal to 2 to the a left 0, because that power set is written the same thing as counter space, and it's so written out that way. That then whether the continuum hypothesis was whether there exists cardinals between those. And then so I learned this, and all I was really interested though was to show that, well, an infinity is an infinitude, so it's impossible to exhaust an infinitude. So I reject this opinion that this infinity is well-founded. So this theory cannot be consistent, because there exists another theory where it is not so, and the numbers obey this other theory. This is rejected, of course. That is not the belief of by and large the field. And so, curiously, transfinite set theory was never introduced to me in any of my prior schooling, all the way up through an undergraduate science degree. It's not really it's not really necessary for anything that was taught in including geometry and real analysis. But it is very well explored, and it's valid in its field. Right? There is a fence. There's another side of the field. I'm coming from the other side of the fence on this issue. And so the first thing that happens when you say, well, there must be functions that are one-on-one and onto between this infinity of the integers and the infinity of the real numbers, for example, the unit interval. And so the response statement will then present one, because the idea is you present an example, and that according to the theorems of uncountability, the anti-diagonal argument and nested intervals, this argument, and this other one called MW, and some of these other forms that I learned quite arduously over a very long time, that the whole idea of these are proofs by contradiction, and so you establish a putative object with the properties, and then it's shown via construction that there exists an object without said properties in those properties, thus it must not be so, the original assumption. So when asked to provide an example of this function between the integers called n for the naturals and 0, 1, the unit interval, well, this function has that it's infinitesimals from 0 to infinity. It's 0, then an infinitesimal next to 0, another one constantly different from that, another one constantly different from that. That this property of being constant, monotone, increasing over the course of this range, and that it's less than any finite difference, results as a function between the natural integers and the unit interval of integers. And that's not unfamiliar, but everybody says, oh, well, we all know that that's just what it looks like when the width of Riemann sums in real analysis vanish, or as they go to 0, and calculus is only good when they go to 0, that they still have analytical character that's non-zero. It's not that it's nil square, not nilpotent, that it still has analytical character, that those become infinitesimals that happen to add up, because over each milieu it still keeps them added up and closer together, sandwiching the limit till such time it's the result, calculus. This is the same sort of thing, except before that. It's just saying, well, I just take the numbers 1 and divide it into half, and then into thirds, and then into dot, dot, dot. till it's divided into 1 over infinities, and it still results, though, that the limit of that function is 1. This function is simply n over d, as n goes to d, and d goes to infinity. So that it's 0, 1, 2 for d equals 2. It's 0, 1, 2, 3 for d equals 3. For d equals 1 million, it's 0, 1, dot, 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 millionths, 1. And the idea is then that it always includes 0, it always includes 1, 0 is always its lower bound, 1 is always its upper bound, and it's so this way that it's a function. Well, then I was told, well, that's not a function, and I had to defer, because to establish it as a function, I would have to establish it as a function in a relation that they can understand. Long story short, I have done so. I have spent many, many years working on establishing basically this factus. And that has gone pretty well, partially because I had the whole side of my fence, that whole side of the fence to myself. Otherwise, I figured this would be totally well explored. But, it would be sort of a career suicide to try to do that in a lot of different realms, where the first thing that would happen is that A, you would be called unmathematical, B, you would say you didn't know your history, C, you'd be accused of cultural insensitivity, and D, then all these other things that go along with being tarred and feathered, or the result of not fitting in these societies, would be that they don't have much cultural sensitivity in terms of their unscientific and unmathematical approaches to a rejection of otherwise the terms. So I had to adopt a very careful course to both keep my original ideas about this that are so, and I defend, and understand. I had to learn all of history and of mathematical foundations as what arose from this to figure out how to address this. And then at least what I was able to do, once I have this function established as a function, and long story short, it's not a Cartesian function, meaning you can't rearrange its elements. So the fact that it's a bijection between the naturals and 0, 1 doesn't break the rest of mathematics that would transitively be related to that, because it becomes a different sort of result, that there does not exist a Cartesian function, so you can't rearrange its elements and otherwise convert it to a different kind of function that would make it simply possible to map any real number segment to the integers and thus violate or break otherwise uncountability. They're two different things. There's also a third thing called signal continuity. So for this line continuity, then there's field continuity as standard. And then signal continuity is the idea that when you have a signal and it has spikes at any given frequency, if you can sample that, you can super sample that at twice the frequency, it results perfect reconstruction. So that's the idea that for a smooth grain or the rationals are huge, that there's a signal frequency, another definition of continuity. Now keep in mind that here mathematics really in the standard world does not have a notion of what's called a continuous domain, though geometry does. It's called a line or a curve. And so the idea of a continuous domain in the world where mathematics has continuous functions and it has topologies and all these usual settings where we have real analysis and standard real analysis, that the only definition of continuity that was so enshrined in the foundations of mathematics so far was the field continuity. Dedekind's. It was a German mathematician who picked up the trail of Cantor and came up with all this formal approbation of it that made it so that it became an authority. That's not, and there are various results about then why Eudoxus, Cauchy, and Dedekind, this model of the complete order field, is insufficient, because basically there's a course of passage of ordinals between 0 and infinity, so there's a course of passage of infinitesimals between 0 and 1 that is constant, monotone, increasing. So what I did then is I had to test this function against each of the proofs otherwise of uncountability. And the thing for the anti-diagonal argument says, well, put these numbers in a list. Now read off the diagonal. Now strike each one of those values and present the anti-diagonal. That's a real number, but it's not in your function because it's not any one of your elements. But here it's like 0.999 and 1. Essentially, that 0.99999, the anti-diagonal is 1, which is always at the end of the function. The anti-diagonal in this case is always at the end of the function. So, briefly, that's solved. And the second one is the nested intervals. And it's like, well, nested intervals was basically, well, take an interval inside, and as you get closer and closer, there'll still be something in there because you haven't satisfied least upper bound, the property of the real numbers, that the center is non-empty. Well, for this function, after you get the first element, there's nothing between them. So actually, this model of real numbers has contiguous real numbers, an Aristotle's continuum. Nobody told me that, oh, that's Aristotle's continuum. All you have to do is prove that you've revived Aristotle's continuum. No, all this has to come from this. Though later I learned that, and I've been put quite a study into the mathematics of infinitesimals and infinities, and the history of it, and the development, and all the requirements and desiderata of rigorous formalization that results a well-defined and sound theory of these things. Similarly for the MW proof, that it became, because this function in its development, after I was able to just get that admitted as a function, fell out of all these proofs. It was different than otherwise any Cartesian function you put her in or out still applies. It's different. So this pleased me greatly because I hadn't been wrong. Now for the power set result, then I basically had to work into a resultant power set of theory that its successor is the order type. The successor in ordinals is called the order type. And it's basically the order type of this number is the next number, the next integer. It's for ordering theory or the ordinals. And so in a theory of ubiquitous ordinals, then it works out that even for the regular, that the missing element of the power set result is empty set, which happens to not be missing this way. So it's just an idea is that in ubiquitous ordinals, with the function being n plus 1, that it works out that happens to close up off to the power set, because in these ubiquitous ordinals, it's a lot like not having a Cartesian space for the function. It's just a line through the diagonal. So again, I was very, very happy that I came to call this function the equivalency function to show that the cardinal equivalency or equipolency of the naturals and this unit interval of these real numbers, which are not standard real numbers, yet they fulfill being a continuous domain, having learned this, that the equivalency function became called the natural/unit equivalency function to reflect that there's no changing its order, and that if you want to map it up then to the rest of the numbers, the real integers, you have to add specifically the integer part on the front, and this is the non-integer part on the back. That the non-integer part, according to this sweep, is so made that sweep was what I named then the general concept, or that sweep is reflecting a couple of different things. First, that the course of passage in constant uniform time is what it accurately models, is a sweep. And then also that for the whole slate of the uncountability proofs, it shows that it's a sweep of those. And the idea thus that there's this prototype function. I first figured it out when I was learning about infinity when I was 7 or 8 years old, and it so results that it corresponds with all the things I ever learned as facts before, and that by carefully disambiguating and examining all the fundamentals of the foundation and getting into all the derivations of thing hold true, that I've been able to arrive at this first definition of continuity. Thus, that the field, the complete order of field, and which is great and it's standard, is a second definition of continuity. Then there's also a third definition of continuity to fulfill that signal reconstruction is perfect. And then these are kind of related, and of course this is turned over by history since forever. And especially so before it was kind of formalized and nailed down for a long time. And this is our fixed tower of proof, the ivory tower. That there's Emile Dubois Raymond, and Raymond has this idea of the long line, and so the long line is basically the continuum with all the real functions in it, not just real numbers, but all real functions, so any relations of variables and real functions. So he basically assigns those in ordering, and there are even more of those, it's called the space of real functions, than there are of, in ordinary theory, of the space of the complete ordered field, or the cardinal of the continuum, or C, because there are more of them. It relates to the power set of those, and there's only the complete line for them to be on. That having a cardinal bigger than the continuum in the continuum itself is another example of why it's so gut-wrenching and heart-wrenching to have to otherwise ignore that, when at the same time, once you do, then it's at least easily accepted that that is one way to go about things, just not the way. There's another side of the fence. I had it all to myself, and I happily tracted it fully, or quite thoroughly, made a little style over it. These bridge results, or the transfer principle, that which we can make so for an element's set, or that which we can make so for this extension, this other extension. So that when it comes to a study of the continuum, I'm very, very familiar then with this sort of approach. And that it involves definitions in function theory, and it involves definitions in after geometry. And that then this equivalency function and sweep has that then at some point in time I wrote what are called the properties of it established as a continuous domain. So there's extent, it's between 0 and 1 inclusive. Density, there's no element in that range that doesn't have it in a neighborhood, another element of the range. And besides they're contiguous, it's just an example of so trivial. It's so utterly trivial that it's first. So there's extent, density, and then completeness is the idea of you have to establish the least upper bound property. Well, luckily, the least upper bound property is established by next. Again, it's trivial, and so it's very remarkable why that is so. And that it was left out is just because it's not a real function, and it doesn't fit in function theory because it's special. And so it's not a Cartesian function where everywhere else in the foundations of mathematics and all of descriptive set theory, functions can be written this way. So it's a system that results being a function. And then finally there's measure 1.0, and for that there's the necessity to implement what's called the sigma algebras. And so sigma algebras basically make for the defining what's the analytical character of the length of this thing. And so I figured out 3 or 4 different sigma algebras for this continuous domain. Now, given those, then I'm able to establish the intermediate value theorem, as when you're crossing a line or what's continuous, you have to cross it, that there's no jumps, it's gapless. So by doing so, then I arrived at having the formal apparatus to then implement a derivation of the intermediate value theorem, which is, from our standard real analysis, then what the fundamental theorem of the derivative and the fundamental theorem of the integral are built on. So this way then, I can do calculus with that. And it's perfectly suited as being a continuous domain. And it almost kind of introduces this theory of continuous domains when you have more than one definition of continuity, because up to then, or as of the day, because of course in history over time this has been very well explored by many mathematicians all over who just never had the luxury of having it all put together, and the luxury of some time to put it together, some luxury of being able to get to the depth to find out what's underneath it, and some luxury of being able to absorb the arrows and slings when going against this way was a very bad idea. So this way, what I arrived at was my fuller definition of continuity. So that's available to anybody in the tens of thousands of postings I've written to Usenet. I've engaged in all these sorts of discussions in a public forum. a vicious fishbowl, as it were, where the fishbowl is an idea from criticism where it's like, let's put that guy in a fishbowl and then we'll tap at it and treat it like a fishbowl, living in the fishbowl or being a fishbowl in the critique, the vicious fishbowl. So anyways, long story short, that's a long story short of the foundations of continua, that there's line continuity, field continuity, and it remains for me to be seen exactly how to formalize, like with sigma algebra and about the functions, the signal continuity, though I did write a paper that at least from an argument about the rationals and rationals being dense, that it does give for the rationals, which are dense on the real number line but not complete, and furthermore, that is the reals are uncountable, that there's not a one-to-one mapping between the rationals and irrationals. I did write a one-page proof of that, and it doesn't mention any other terms. It's in its own little world, but at least there's something there that constructively, where we, at the end of the day, we want constructive proofs, the full proof from the foundations of all this, constructively establishes for signal continuity that it's also a thing, and then it's kind of just pending sigma algebras, but it can also reuse all of the fields as sigma algebras. What's interesting though would be its own sigma algebras, because then for the sigma algebras, that works for measure theory. And measure theory, when we talk about the topology and all this invariant theory and continuity laws and all these things, what go along with it after the fundamental theorems of analysis, that is carried right along. Well, that's a brief story about a long story, and it kind of well sums it up. That then the continuum of Herman Wiles' critical examination of the foundation analysis has that he provides a linear narrative of sorts about the thinking that goes into kind of the ends and the middle and the stitching of when over time these kinds of things that became great consternation to lots of different thinkers like Skolem and Lowenheim or Hausdorff and Vitali, that these days when I talk about revitalizing measure theory, it's along these lines. And it gets into real non-standard formulas and stuff that does not behave at infinity, but is real. Or, which I have not mentioned here, but may at a later date. Or Hausdorff is like the constructible continuum is continuous and constructible. And then there's like a Bishop and Chang who established this sort of thing about transfer principle and otherwise said, hey, at least this is a thing, if not necessarily saying plus, the standard foundation has to shift a little bit. They would not go that far. But then there's Bishop and Chang and Vitali and Hausdorff and Skolem and Lowenheim and Levy, who gave for this, like, I can make a countable model of this uncountable thing and make these extensions and contractions of it in an ordinal sense. Then that there's also Cohen and after the continuum hypothesis, which is mentioned, which is, are there cardinals between the cardinals of Aleph 0 and C? Or is Aleph 1 equal to 2 to the Aleph 0, or are there others? The continuum hypothesis, or the generalized continuum hypothesis, that it is so, that is so, and the whole cumulative hierarchy of these things. So what Cohen established after Gödel was that the continuum hypothesis was independent of the theorems of ZF, that it cannot be proved either way given the theorems of ZF. Now, one thing that I don't know in this technique is called forcing, and so he basically establishes a model up above, and he says, well, this model is that, and then this model is the other one, so you can have this model, it's always, he establishes an arbitrary inequality, and thus it is so that whether or not the continuum hypothesis is true is actually only a conjecture in ZF the theory, because it's independent of ZF the theory, and thus that it's independent of the axioms of ZF theories, that he so proved it and everybody accepted, that it would require a different theory to establish the conditions on under which it holds or does not hold. So that gets back into basically that's a statement in ubiquitous ordinals, because his model, that his cousin model, or as he puts it, what it is, that it's he reverses the order at the end. And it's a little bit of sleight of hand because he introduces an axiom to make it so, but he just kind of did so at the end of the whole development so that nobody really knew that without actually following along the development, that by authority he left the door open. Cohen's independence of the continuum hypothesis is a lot in that sense like Gödel's incompleteness theorems, read the way that beyond those there is a theorem, that what we have is just independent of those, or vice versa. So that gets into today then, where some people even think the world is just finite, or that there is no real continuous in that. These are what we call retrofinitists. And you can be a conscientious ultra-finitist, and that's fine. You're working in a realm of discrete numbers, and you made it so, and you formalize it so, and it's constructively so, and you're welcome to it. But there is a real continuum, and there are real mathematics beyond the standard, and not just as modeled by the standard. For example, as the equivalency function perfectly well is modeled by the standard, or as a distribution, or a functional, or what. That, going forward, I had felt I had really well covered the study of the continuous and discrete in the foundations, and in fact, for my strong mathematical Platonism and all this, I'm pretty sure I can't have it any other way. But it is inclusive of at least these three definitions of continuity, not just one, couched in a milieu and framework of the long line of continuity. So that then when I look back at Duns Scotus and Baruch Spinoza and their discussions on infinity and the integer continuum, and then when I think about, Peano, who's most well known for his integers, but also has a model of infinitesimals, or Dodgson, the guy who wrote Alice in Wonderland, Lewis Carroll, one of his flights of fancy was a mathematical description of infinitesimals with non-analytical character, illustrating that the continuum in the uncountable is so totally rich to have all these kinds of infinitesimals that don't have analytical character, where these ones from the equivalency function fundamentally are analytical character. That there's Veronese and Stoltz and Aristotle and Archimedes. When we talk about an Archimedean field, there's to keep in mind that first Archimedes was like, there's more than finite. There's more than finite. And they're like, okay, Archimedes, what's infinity? He's like, they're all finite. The Archimedean field is, to be a non-Archimedean field, it was a non-Archimedean field. Thus that when we arrive at more of the considerations of what's to be the technical underpinning of a theory of everything, then that gets more into our readings of the philosophical explanations and these kinds of things. Well then, that was the talk for today. Continuity. Good afternoon.